Okay, we're going to take a little time now to talk about oscillations and oscillatory behavior, but more specifically, we're going to talk about it in mathematical terms. So we're going to discuss the sine and cosine functions just briefly. And the reason we want to do this is that we're working with these constant coefficient linear or homogeneous equations, and we're looking for functions that when we take derivatives, we get something similar. And we should expect to see sine and cosine functions. The reason being is when you start taking derivatives of these things, you take derivatives of cosines, you're going to get sines. When you take derivatives of sines, you're going to get cosines. So taking derivatives and putting them back into this original equation, we should expect to see cosines and sine solutions appear in some situations. Now, having said that, we have been focusing on solutions of the form of an exponential function. At the same time, because of Euler's formula, it's going to turn out that by focusing in on things of this nature, we're going to sweep up and be able to get cosines and sines. So the question is, how do we do that? Before we get into those details, though, we need to just talk about cosines and sines and know what to expect when they pop up. So in terms of cosine, so if I have cosine of omega t as a function of t, it's going to look something like this. It's going to have some period over which it repeats. And so on this period, this function is going to repeat over and over and over again. And the question is what is the period if you're given this omega that's appeared here? So you have cosine of omega t. You've got this cosine function, and you're giving it as a whole omega t. At the same time, cosine itself, as you go from 0 to 2 pi, will go through one whole cycle. So the idea is that you look at the whole argument. So you look at everything that goes inside here, in this case the omega t, and you want to ask for what time will that go through one whole cycle. So what do we have? We have cosine of omega t. We know that as omega t goes from 0 to 2 pi, the t will go through one whole period. So in terms of finding out this period, we know that when t is 0, we get that. When we plug in the period, we should get this. So for the period, should satisfy this, or t equals 2 pi over omega. Now, having said that, it's more important to understand what this means, because there are going to be some times where you're given omega and asked to find the period, and sometimes you're going to be asked to find omega given the period. So knowing how to work with this and what it means is going to help you figure out how to work with a given system. And just to be complete, note the same kind of thing is going to work with a sine. The only difference is that it's going to be shifted a bit. And as the t goes from 0 through the period, sine is going to go through one whole cycle. So we have sine of something. This something, as it goes from 0 to 2 pi, that will go through one whole cycle. Right? And in this case, the something is omega t. So when t is 0, we get this. And when t is equal to the period, notice we get exactly the same relationship. So recognizing this and knowing how to deal with this is going to be extremely important. And again, we started off talking about things like this, and it's not clear what this has to do with sines and cosines. But we're going to find out there are going to be situations where the n is a complex number. Oops. So, and if I have e to the I omega t, we can use Euler's formula to write things out in that form, right? And the way we saw that before, the way it's usually presented is like this. But what's going to happen is instead of theta, our theta is going to look like omega times t. So everywhere I see a theta here, I'm going to replace it with an omega t. Okay. So where's this going? So we had second order constant coefficient, homogeneous equation, so we had a 0 there. We end up working with a quadratic function that looks something like this. And if we have distinct roots, we have something like this. So again, this is if the roots are distinct. And we also saw that if we had a repeated root, well, that's one of the roots, and then the other one we can find by just multiplying by t. What we have not yet seen is complex roots. And what's going to be important about complex roots is that it's actually the exact same thing as this, only there's going to be a little bit of extra algebra. And what we're going to find is we're going to have sines and cosines. So in this situation, we're going to have complex roots. So again, before we called this case 1, we called this case 2, and now we're ready to talk about case 3. Before we do this, in the context of DEs, we're going to explore this a little more and recognize that we're going to look at a situation where we're going to have z equals d plus omega I. Right? And this is coming from finding the roots of something like this. And if you use the quadratic equation, we have that. And I can break this up into two pieces. And if the thing in here is negative, then this thing is going to come from that piece. This omega is going to come from this piece, but we've got to be careful because there's going to be a negative sign, and we'll see how that negative sign manifests itself later. But before we do that, let's just go back and remind ourselves what's going on with this. So for example, if I have z equals minus 3 plus 2i, what did we say? If I look at this in terms of the, complex plane, the horizontal axis is the real numbers, vertical axis is the imaginary numbers. So I can think of this as the horizontal is going to be often minus 1, 2, 3, and the vertical is going to be in that direction. So this number I can think of in that form, and I can think of this as having some angle away from the positive real axis and some length r. And we had z equals minus 3 plus 2i. We can write it as r cosine theta for the real part plus I r sine theta for the imaginary part. And if I factor out the r, I have this. And this thing we can now write using Euler's formula. Okay. So this idea that we can look at this and think of these numbers as rectangular form, polar form, and Euler form is going to be really important. So what happens now if I have e to the zt? And suppose z is going to be d plus I omega. And again, we're assuming d is real and omega is real. So if I have e to the zt, I can right now replace the z with the d plus I omega t. I can multiply the t through. Now I can break this into two parts because I have e to the something plus something. I can write it as e to the first thing times e to the second thing. And this is exactly what we had before. This is the Euler form for a complex number. And notice I can think of this as the radius. So if I expand this out, I can go e to the dt, now using Euler's formula. It is now in this form. So the question now is, how do I interpret this? Well, this I can think of as my radius. This thing can either grow or decay. So if d is positive, it's going to grow. If d is negative, it's going to decay. And it's going to stay the same if d equals 0. It's not going to change. This part right here, cosine omega t and sine omega t, that's going to oscillate in exactly the same way we saw before by itself. But what happens now here is this amplitude is going to change. So if I just look at this first part, if I multiply that through, I get e to the at, sorry, that should be e to the dt cosine over time. This is going to oscillate like we've already saw. This is going to be the amplitude. And if d is greater than 0, that amplitude is going to get larger. And when I multiply by the cosine omega t, it's going to oscillate but grow extremely large. Likewise, so e to the dt, if I look at the case d less than 0, now, oops, and this is going to be e to the dt cosine of omega t. If d is less than 0, this e to the dt is going to decay to 0. So the amplitude gets close to 0. And so now this thing, as time goes on, I multiply that cosine, it's going to decay and get really close to 0. Okay. All right, now we're going to play some heavy algebra games. All right, so we are looking at solutions now for our differential equations that are going to be in the form c1 e to the z1t plus c2 e to the z2t. We have n is going to be minus b over 2a plus or minus 1 over 2a square root of b squared minus 4ac. That's coming straight from what we saw before, from the roots of a n squared plus bn plus c equals 0. We are going to focus on the special case where that's going to be real, and if b squared minus 4a is negative, that's imaginary. So our solution then is going to look like n equals d plus or minus I omega, where omega is going to be what's associated with this, and then d is equal to minus b over 2a. So in this context, my Z1 is going to be d plus I omega, and my Z2 is going to be d minus I omega. Okay. So the solution to my differential equation is going to be C1 e to the Z1t plus C2 e to the Z2t. And it's going to be extremely important for me to be able to look at this solution and understand what it means. Okay, so I'm going to plug in what I know about Z1. Z1 is going to be d plus I omega t. Z2 is d minus I omega t. And this is going to carry on exactly like what we saw before, except there's going to be a minus sign there. So it's going to be CE, I'll multiply the t through. And so I get dt plus I omega t. And I'm going to do the same thing here. I'm going to multiply the t through, but I'm going to get a dt minus I omega t is the difference. Since this is e to the something plus something, I can write this as the product of e to the dt times e to the I omega t. And here I can write this as e to the dt, but now this is going to be an e to the I negative I omega t. This term and this term is the same, so I can factor that out. So that's going to give me C1 e to the I omega t plus C2 e to the minus I omega t. And now I can use my Euler's formula. So this thing on the outside stays the same. C1 times e to the I omega t. This is going to be cosine of omega t plus I sine of omega t. And plus C2. Now this is going to be, because everywhere I see an omega t, this is now a negative omega t. So this becomes cosine of minus omega t plus I sine of minus omega t. I've got to figure out how to deal with these two terms, because it would be nice to write them in terms of cosine of omega t and sine of omega t so that I can collect them together. Fortunately, I know cosine is an even function and sine is an odd function. Right? That means that cosine of minus omega t is the same as cosine of omega t, and sine of minus omega t is minus sine of omega t. So now my solution then I can write as C1 cosine of omega t plus C1 I sine of omega t. So I just multiplied the C1 through there. Here, cosine of minus omega t is just cosine of omega t, so that becomes C2 cosine of omega t. Sine of minus omega t is minus that. So when I multiply that C2, I get minus C2I sine of omega t. And now, notice I've got a cosine here and a cosine here. So let me collect those two. And here I've got a sine and a sine. So let me collect those two separately. If I do that, my x of t, so for now for the cosine terms, I've got C1 cosine of omega t plus C2 cosine of omega t. The two sine terms look like minus I C1 sine of omega t minus I C2 sine of omega t. And now for the cosine terms, if I can factor out that cosine, I'm going to get a C1 plus C2. For the sine terms, I've got a sine there and a sine there, so I can factor that out. I'm going to get a minus I C1 minus I C2. C1 and C2s are just some constants. I don't know what they are. All I know is that they're constants. So that means C1 plus C2 is a constant, and IC1 minus IC2 is a constant. I don't know what those are. Let me just call that K1, and this called K2. Oops, and I forgot something. Notice in my original I than e to the at. So I need an e to the at out here for both of these. So I'm going to get e to the at. I'm going to have k1 cosine of omega t plus k2 sine of omega t, all multiplied by, oops, I called that d on the previous page, e to the dt. Sorry about that. All right, and we know that if d is greater than 0, the amplitude grows. If d is less than 0, the amplitude decays. And if the amplitude is, or if d is equal to 0, it doesn't change. Here, I'm going to have oscillations, and the period is going to be equal to 2 pi over omega, or, more importantly, I have omega t equals 2 pi, which relates my omega and period together. Okay. So, what's going to happen now in practice is that we're going to have ax double dot plus bx prime plus cx equals 0. A, b, and c are constants, so it's constant coefficient, it's linear, and it's homogeneous because of the 0. I'm going to make an assumption that I have an exponential function for the solution, and I plug it in, and it's going to boil down to this thing. My n is going to be minus b plus or minus b squared minus 4ac over 2a. If b squared minus 4ac is positive, we've already figured out how to deal with that. We can deal with that. We have two distinct real roots. If b squared minus 4ac is 0, I have a repeated root, and again, we know how to deal with that. What we've not dealt with is the case when b squared minus 4ac is less than 0. In this case, though, I know that I can write n is minus b over 2a plus or minus 1 over 2a multiplied by the square root of b squared minus 4ac. This is a negative number. I don't like taking the square root of negative numbers. I'd rather think about this as I times a real number. So if I factor out a minus 1, I flip the sign. So notice this expression is equal to minus the quantity 4ac minus b squared. If I multiply that through, I get minus 4ac plus b squared. If b squared minus 4ac is less than 0, that means the negative of that is greater than 0. So this thing right here is greater than 0. So I'm going to have n equals minus b over 2a plus or minus 1 over 2a times the square root of minus 4ac minus b squared. Let's take a closer look at that. So what do I have? I'm going to have my n is minus b over 2a plus or minus 1 over 2a square root of minus the quantity 4ac minus b squared. And I know that 4ac minus b squared is positive from my assumption that b squared minus 4ac is negative. I can factor out that minus 1. And if I do that, that becomes the square root of minus 1. And we have another way of expressing square root of negative 1. We call that I. And notice this is now expressed in the form of a real number. If we call that d, this is now a real number because the square root of 4ac minus b squared is a real number because 4ac minus b squared is positive. I can call this omega. right? So my E I can write as d plus or minus I omega. And that means my x of t is going to be some c1 e to the d plus I omega t plus c2 e to the d minus I omega t. And we just went through and did all the algebra to find out that we can write this as e to the dt is equal to k1 cosine omega t plus k2 sine of omega t. And again, I can immediately interpret the amplitude of the oscillations in terms of the real part, and I can figure out the period of the oscillations and the nature of the oscillations based on the imaginary part. So given that n is equal to d plus or minus I omega, if d is, you should immediately recognize that if d is negative, we get exponential decay. If d is positive, we get exponential growth. And the imaginary part tells us about the oscillations where omega t is 2 pi, where t is the period of the oscillations.